Hello everyone. Today I'm going to present our skeleton-aware multi-modal sign language recognition model, which is also called SAM-SLR, by which we won the first rank in the CVPR isolated sign language challenge in both RGB and RGBD checks. First, I'm going to introduce myself and our team. My name is Songyao Jiang. I'm a fifth-year PhD student and the team leader of our competition team. Our team members include Bin, Lichen, Yue, Kunpeng, and Professor Raymond Fu. We are from SMILE Lab at Northeastern University in Boston, Massachusetts. Our code has been made to public in a GitHub repo, and we also have an accepted paper to the workshop. You can check out the paper and the workshop to find more details. Comparing with other video classification tasks, such as action recognition, SLR is a more challenging problem for the following reasons. First, sign language requires both global body motion and delicate arm or hand gestures to accurately express its meaning. Second, similar gestures can even impose various meanings depending on the number of repetitions. Third, different signers may perform sign language differently. For example, different signers may perform in different speed with different localism. They may even have different body shape and either be left-hander or right-handers. In our preliminary study, we are inspired by some recent development of action recognition. I find that the skeleton-based method is becoming more popular in action recognition. The skeleton-based methods are invariant to background and action performers and can be strong complements to the traditional RGB or RGBD-based methods. In action recognition, state-of-the-art accuracy is always obtained by assembling different modalities. Our assumption is that different modalities capture different information, and training separate models on different modalities will complement each other and improve the overall performance. Here we show the pipelines of our proposed framework. Given RGB and depth videos, first, we pre-process the original RGB and depth videos into corresponding modalities. We have 6 modalities in total. For RGB videos, we process them into pose key points, pose features, RGB frames, and optical flows. For the depth videos, we convert them to HHA representation. We also extract optical flow from the depth videos. Then we have 3 types of models to deal with those modalities. We assemble them together to make our final prediction. For RGB check, we assemble the predictions obtained from key point path, feature path, RGB path, and RGB optical flow. For the RGBD check, we add the additional prediction from HHA and depth flow path to further boost the accuracy. Since the dataset doesn't contain any ground truth key points, we need to use a pre-trained human pose estimator to obtain the key points. For traditional 2D human pose estimation, it only predicts 16 or 17 points, which do not contain any key points of hands. However, hand key points play an important role in recognizing sign language. A straightforward solution is to use a separate hand pose estimator to obtain hand key point. The problem of such approach is that the hand pose estimator relies on the accurate hand detector, but in our experiment, we find that the hand detector fails very easily due to the motion blur and low resolution of the video. So instead of using separate hand pose estimator, we utilize the recent development of whole body pose estimator. The whole body pose estimator has global information of human body and therefore provides faithful and stable result even under motion blur. From the whole body key points, we construct a spatial temporal graph for the sign language recognition. We use a similar approach as in the skeleton-based action recognition. However, too many nodes introduce extra noise into the graph and harm the recognition rate. So we apply a graph reduction technique and reduce the 133 nodes to only 27 nodes. The remaining graph contains 10 nodes for each hand and 7 nodes for the upper body. Inspired by a recent paper on action recognition, we construct our basic SLGCN block containing a decoupling spatial convolution network, a temporal convolutional network, and the STC attention module. We also use a multi-stream workflow, including joint stream, bound stream, joint motion, and bound motion streams to further improve the performance. The performance of SLGCN is shown below. First, we evaluate multi-stream performance on the validation set, and the multi-stream approach further improves the recognition rate by 0.4. We also conduct ablation studies to show the contribution of different modal components. From the study, we can see that all the components contribute to the recognition rate. In addition to the whole body key points, we also use the features extracted from the pre-trained whole body pose estimator. We propose a separatable spatial temporal convolution network, in short SSTCN, to capture the features. The motivation is that the factorization of 3D convolution will be easier to optimize compared to full 3D filters, where appearance and dynamics are jointly intertwined. So for the other modalities, RGB frames, optical flow, HHA, we use a 3D convolutional neural network to capture the spatial and temporal information from those modalities. We select our baseline as the ResNet 2+1D 18. This model is easy to train and hard to overfit. Based on the baseline model, we made the following modification. We replaced the ReLU activation with the switch activation. We adapt the label smoothing to further avoid the overfitting problem. We import weights trained on connected 300 action recognition dataset. Then we pre-train the model on Chinese Sign Language dataset. Pre-training the model on the datasets improves the accuracy as shown in the table. We also conduct ablation studies without label smoothing, without switch activation, or using a ResNet 3D 18 backbone instead of the 2+1D. We use a simple example method by adding up class scores with the weights. The alpha are the hyperparameters which can be tuned. When we tune the hyperparameters, we tune the parameters on validation set. Here's a rule of thumb. Higher accuracy models are always given larger weights. Here's the overall performance of different modalities and their examples. Examples of multi-modalities are shown on the right-hand side. The overall performance during test phase are shown below. During test phase, we fine-tune our model using the validation set. The fine-tuned results further improve the recognition rate in both RGB and RGBD check. We achieved 98.42 in RGB check and 98.53 in RGBD check. In conclusion, we propose a novel skeleton-aware multimodal SLR framework to take advantage of multimodal information towards effective SLR. Our multimodal example result achieved the state-of-the-art performance and won the challenge in both RGB and RGBD checks. That's the end of the presentation. Thank you.